In class on Friday, we left off with this example with the magnifying glass, and we didn't get to talk about the last few slides. So I'll post a video here going through those examples and slides. So the first thing here is image formation with diverging lenses. And the big difference between image formation with converging versus diverging lenses is parallel rays that come into diverging lenses now diverge on the opposite side, and we extrapolate these rays to figure out the focal point. And notice that the focal point for diverging lenses is negative. So the focal length of a diverging lens is going to be a negative value. Something to keep in mind, if a problem statement says you have a diverging lens with focal length 10 centimeters, they're just giving you the magnitude of the focal length. You need to use the fact that it's a diverging lens to determine whether the focal length that you're using in the formula for the equation, the lenses equation, is positive or negative based on what type of lens it is. Okay, so let's practice some basically image formation using rays. So these are the three rays that we can draw to form our image. The first ray is parallel to the axis and diverges along a line through the near focal point. So just to remind you all, this is the near focal point, this is the far focal point. So we'll go ahead and start with a parallel ray, and also, as I mentioned in class, it's easiest to do these problems if you go ahead and draw a vertical line through the center of the lens and draw your rays up to that point. Okay, so parallel ray comes in and it diverges through a line that goes through the near focal point. So I'll go ahead and first draw a line through the near focal point, just to get a line through here. All right, and then I know that as this ray diverges, so as this ray diverges, it's going to diverge out like this. All right, so this thin line I drew here is just to figure out where's the line along which it's going to diverge. Well, I have to basically draw from the near focal point to the point where this parallel ray hit my lens. Okay, so that's the very first ray. That one's done. Second ray is a ray along a line towards the far focal point, and it emerges parallel. So this one's a tricky one. So we need a ray along the line that is towards the far focal point. So we're starting here, and I'm going to draw that line in a thin black color. So the line starts at the tip of the object and connects the far focal point. Okay, so the ray is incoming along here, and I'll draw the incoming ray in a darker black, and then it emerges parallel on the other side. So the reason why I needed to draw this first line is to basically figure out what path do I follow to the lens, and then that ray is going parallel. And let's think about what's happening here. You can imagine a parallel ray coming in this way, and you know on the other side of the lens it's going to diverge. To figure out what line along which it diverges, it has to come back to the focal point here. So this is the reason why we first draw a line from the top of the object to the focal point, and then know that the ray is coming out parallel to the optical axis. So there's our two rays so far. So our rays are emerging on the other side of the lens here and here. So technically, first we already see that these are diverging rays, so we're going to have to follow these back, extrapolate, and figure out where the image forms. But let's go ahead and draw the third ray too, so that we can see that they all meet. So a ray through the center of the lens that doesn't bend. So the last ray is starting here, goes through the center of the lens, and it does not bend. So there is our last ray. So I'm going to go ahead and highlight our three rays just to point these out. So there's the first diverging ray. 1, 2, and 3. Now to figure out where our image would form, I need to go ahead and extrapolate these backwards. So I'll draw a dotted line going back, draw a dotted line here going back, and then draw a dotted line here going back from the ray, and we see that they all meet here. So we know that our image is going to be just to the right of this near focal point. And let's go ahead and figure out what type of image this is. Well, any image that is being formed from extrapolated rays. The rays aren't actually converging here. You know that this is a virtual image. Upright, because it's upright, we can see that. And then finally, we know that this image is smaller than the object. And if we were to have actual numbers for the focal length, have an actual number for the object distance, what do we expect the image distance to be? Do we expect it to be positive or negative? And hopefully you realize that a virtual image gives us a image distance that is going to be negative. So when the image forms on the same side as your object, this is a virtual image here, which has a negative image distance. All right, now let's go on. So here's just a nice version of that ray diagram drawn here. Now let's try this practice problem. So in this practice problem, we have a diverging lens with a focal length of 50 centimeters. So as I just mentioned, the moment the question tells us that it's a diverging lens, even though this is given to us as a positive value, we need to realize when we're using the equations, we need to plug this in as a focal length of minus 50 centimeters. So we have a divergent length with a focal length of 50 centimeters. It's placed 100 centimeters from a flower. So our object here is some flower that is 100 centimeters from the lens. Where is the image? That's what the question is asking. So we would like to find DI. We're told that the object distance is 100 centimeters. And we know the focal length. So we'll go ahead and use our equation. 1 over the focal length is equal to 1 over the distance to the object plus 1 over the image distance. And then since we're solving for image distance, let's just go ahead and try to isolate image distance. That will be 1 over f minus 1 over object distance. And then image distance is going to be basically 1 over f minus 1 over do, all to the minus 1. So let's just go ahead and plug everything in. So our focal length is 50, so we get 1 over negative 50. And we can go ahead and plug everything in centimeters and get our answer in centimeters. If you want to plug in everything in meters and SI units, then you expect an answer out in meters. So I'll go ahead and keep things in centimeters here. So 1 over negative 50 minus 1 over 100, all to the minus 1. So now I need a common denominator. I have to multiply top and bottom of this fraction by 2. So I get that the image distance is negative 2 over 100 minus 1 over 100, all to the minus 1. Notice all I did is I took this minus sign and applied it to my numerator. It doesn't matter if I have a negative multiplied by a fraction, whether I apply that to the numerator or denominator. Okay. All right. And then this is equal to negative 3 over 100, all to the minus 1, which gives us 100 divided by 3, still negative. And that's negative 33.3, about 33.3 centimeters. Okay, so we're getting a negative image distance. We're getting a virtual image. Let's go ahead and confirm if this checks out. So let's draw a ray diagram. We have a diverging lens. So let's go ahead and draw a diverging lens. All right. And then we have a focal length of 50 centimeters. So what I'm going to do, first is just start by drawing a vertical line off of which I'm going to have all my rays converging, diverging, etc. And then here's how I will try to draw my diagram to be as precise as possible. So let's just say this much here. Oops. Let's say this distance is 50 centimeters. So I'm gonna just copy and paste that a few times. All right, so, oh no, that's not even a straight line. Let's try that again. So do it in a different color. All right, I'm gonna call that my measure for 50 centimeters. So I'll copy this and paste. So there's 50 centimeters. I'll put a tick mark here. Then another 50 centimeters. Okay, put a tick mark here. And then another 50 centimeters. Put a tick mark here. And then finally, last 50 centimeters. All right, so without really having to measure things, it's nice that I can, and honestly, your ray diagrams do not need to be this precise. It just helps. Let's go ahead and measure, label this point here, our focal point, our near and far focal points. And then we know that the flower is placed at 100 centimeters. So let's say here's my flower. I'm just gonna represent it with a boring arrow. And now, as I'm drawing my ray diagram, I'm going to practice these three rays. So first, a ray that's parallel and then diverges along the near focal point. So let's start with that. We have our parallel line, and then that ray is going to have to diverge and follow basically this line. So it diverges and follows this line. Great, so incoming, outgoing. Then the next ray is a ray along the line towards the far focal point. So I know I'm gonna need a line going through the far focal point, so I'll just draw a dim line going through there. So the incoming ray is following this up to the mirror, up to the lens. Oops, this is a little harder to draw. So there it is. And then it's gonna come out parallel to my optical axis. So it comes out parallel to the optical axis. So incoming, outgoing. And then the last ray, this is our easy one, it just goes through the center of the lens without any bending. There it is. All right, so again, I'll highlight my outgoing rays in green so we can follow them. Outgoing 1, outgoing 2, outgoing 3. Notice they diverge. So for us to figure out where they meet, we're gonna need to extrapolate. Okay, this extrapolates back here, extrapolates back here. So they're all meeting at this point. So sure enough, I have my image forming here. And if I am saying that here to here is 50 centimeters, I can imagine this distance being 33.3 centimeters. And the reason why it's negative is because this is a virtual image. So we have a virtual image, and it makes sense that we have a negative image distance. And then if I were to calculate the magnification, which we're asked to do, let's go ahead and just do that real quick. Magnification is equal to minus image distance over object distance. So minus image distance, which is 33.3 centimeters, over object distance, which is 100 centimeters. This gives us about 0.33. Notice that this number is both positive and smaller than 1. The fact that it's positive tells us this is a upright image, and then the fact that it's smaller than 1 tells us that the image is physically smaller than the object. And how much smaller? Well, it's 33% the size of the original object, and this is sure enough about a third of the original object. All right, so hopefully this will help out with you finishing up some homework. And then the last thing that I want to bring your attention to is the lens maker's equation. This is an equation we're gonna talk about more in class tomorrow. So here's the idea. The focal length of any thin lens is based on the following parameters. So this is going to be the focal length of some lens. These two are both supposed to be an index of refraction. Technically, it's n lens minus n medium, what medium the lens is in. We're going to go ahead and just assume that we're putting our lenses in air, and that's why I've plugged in a 1 here. But let's say you were to put your lens inside of a liquid like water, then to figure out the focal length of your lens in water, you would replace 1 with the index of refraction of water. And then there's R1 and R2. These are the tricky ones because we have to not only measure the radius of curvature, or not measure physically, but like know the radius of curvature. We need to know whether these values are positive or negative. So they can be either positive or negative. So which one's R1? So if we're looking at this lens here, meaning we might put an object somewhere here, the first surface that you run into, so surface on the left, or the first surface, that is our R1 surface. And then the second surface, the surface on the right, on the right is our R2 surface. Now, whether they're positive or negative, we check for the following. Well, a curved surface here forms a circle like this, where its center of curvature is on the other side of the lens. A center of curvature on this side of the lens is a positive radius of curvature. So if I have a object here, light incoming from here, a radius of curvature on this side, or a focal point on this side, are considered positive for lenses. So in this case, R1 for us is a positive value. And then if we take a look at surface 2, well, surface 2 is part of a circle that, if you complete it, looks like this. And its center of curvature is on the same side as where the light is coming from. So R2 for us is going to be a negative value. So the rule of thumb you can use is if the center of curvature from that specific surface is on the same side as where the light's coming from or where the object is, then that's a negative radius of curvature. And then if the surface gives you a radius of curvature on the other side of the lens or on the other side of where the light's incoming, then that is a positive radius of curvature. Okay, so we're going to talk about this one more time in lecture tomorrow, but if you want to get a little bit more progress made on your homework, this will be helpful.